So here's another example of finding an average atomic mass for an element. So I came up with a fictional element Z. And I just wanted to use this example to kind of recap what an isotope is, which helps explain why it takes a lot of work by scientists to establish an average atomic mass, because the average atomic mass of an element takes into account that all elements have more than one form. Now let's recap that if it's a particular element, they all have to have the same number of protons. So let's say that element Z has 12 protons. If this proton number changes, it's no longer element Z, it's something else. But what can vary is the number of neutrons. And you can tell that if element Z has a form of Z24, there's 12 protons, then that means that mass of 24 minus 12 protons means 12 neutrons. So from there we can probably guess that Z25, having one more atomic mass unit number than 24, must have an extra neutron. And then Z26 would have 2 extra neutrons. So that explains isotopes. They're just atoms of an element that have different numbers of neutrons. So in this case, scientists have rigorously worked out a fairly precise mass for each one of these isotopes of element Z. Element Z24, his weight is 23.93, 25 is 24.98, 26 is 25.91. And through tons of research and chemical analysis, lab analysis, they found that Z24 occurs 73.25% of all the known element Z samples that have been assayed around the world by scientists, while Z25 is a representation of 13.42% of all the samples. Z26 makes up 13.33% of all samples. They, of course, should always add up to 100% because percent is Latin that literally means per 100. So what we want to do is make a composite value of all this representation, because we can make an assumption that if we have some Z and we want to do lab work with Z, it's going to be a mixture of these 3 isotopes found in there, and that they will roughly have this ratio. Is that guarantee? No, but that's a safe assumption. So what we're making is a weighted average. A weighted average differs from a standard mean average. If we had a mean average, we would simply take these 3 samples up and divide by 3. But a weighted average means that we don't give every single value that goes in the average the same worth, the same importance. We weight them according to their overall value. In this case, the overall value is what percent they make up in nature. So to do this, we multiply each by its percent representation, and then we take the 3 products and sum them. But to do that, as we always have to do with percents, if we want to work through the problems, we have to turn them back into ratios by multiplying, moving the decimal 2 places left. If we don't, we'll get these outrageously large numbers. So we do that in these 3 cases, and we get these products, and we sum them up, and then it's time to round. And since all of the numbers, the values that went in are 4 digits, we can round to 4 digits. That seems logical to us. The last thing we do is we look at the answer and say, does it make sense? And whether it's right or wrong, whether we made a mistake or not, makes sense because 24.33 is within the range of the values represented. It's somewhere between the low value and the high. If we had a value outside of that range, that would make no sense. It doesn't matter whether you have a weighted average or a regular mean average. You can't have an average that's higher or lower than any of the numbers that went into the average. That's illogical. If you do, it probably is a good sign that you punched something in the calculator wrong. You need to do the work again. But at any rate, this is another example of finding the average atomic mass for a particular element, and also reminding us why that is the case, why that's important, and what in nature, in the atomic structure of an atom, drives these differences between different forms of an element that we call isotopes. And that difference is different numbers of neutrons in those atoms.